Welcome to another National Training Center Tech Byte. Today's Tech Byte is on protection and control, the theory and math associated with it, and specifically the simulation of the open delta potential transformer with test equipment. Tech Bytes are typically quick videos that'll be from 3 to 8 minutes in duration to cover a very specific topic or issues associated with the world of electricity. This is actually one of our longer Tech Bytes. This one's going to run about 15 minutes just because of the complexity of the content. This Tech Byte topic is associated with protective relays and metering as it pertains to the simulation of the open delta PT configuration with relay test equipment. I hope this is helpful to you. So what is the open delta? Let's start with the fact that the open delta connection transformer uses two single-phase transformers to provide a three-phase supply to the load. An open delta connection system is also called a VV system, or open delta. The open delta connection systems are usually only used in emergency conditions as their efficiency is low when compared to a delta-delta for power transformers. We see this configuration more often in switchgear potential transformers at the distribution level for secondary metering and protective relays. Before we get into the use of the open delta in medium voltage switchgear for metering and protection, I want to address briefly the use of the open delta configuration in the power industry. In power, when we are using three single transformers in a closed delta, we may have a failure and need to run on just two transformers. We connect these open delta and can produce 0.577 times the rating of the closed delta system. In other words, by connecting the two transformers that are remaining in an open delta, we can still produce three-phase power, but we're going to produce it at a derated or reduced power level. With three 1.5 MVA transformers, we would have 4.5 MVA. 0.577 times 4.5 MVA would be 2.6 MVA. Another way to look at this would be the square root of 3 times the value of just one of them at 1.5 MVA would equal 2.6 MVA. These two different methods of looking at how to do this calculation both indicate the same thing. When we take a three-phase delta transformer power system, we remove a transformer and we connect the remaining two into an open delta. What we get out of this is three-phase power on the secondary at a reduced MVA rating of 2.6 MVA versus the previous 4.5 MVA with all three. This is really not part of this lesson, but I wanted just to quickly address it since this is another application of the open delta. Here we have a three-line diagram of our open delta potential transformers. If you look at this, you'll see that we're using two PTs tied to our bus to generate three-phase voltage, which is phase to phase. We're also using three CTs that are connected in a Y connection. So the delta to Y connection is going to produce a 30-degree phase shift. So once we develop our voltages, there will be a 30-degree phase shift between the voltage and the current. Now you can see this in VAB voltage up above is 120 volts at plus 30, whereas A phase current below is at 0, which is lagging AB voltage by 30 degrees. You'll see on BC voltage, which is 270, again, the B phase voltage is lagging by 30 degrees. And then you'll see the same thing on VCA, which is plus 150 versus 120, which again is 30 degrees. So this is basically the connection that we're going to be looking at, and we're going to move on and start looking at our test equipment setup. First, you can see here with the Manta, we're only going to use two of the voltages to represent our two PTs. In this case, we want to represent our metering at unity power factor or a pure resistive load, whereas voltage and current are in phase. Since we'll use the current as our reference point, we need to start by setting all of our currents at angles of 0, plus 240, which is the same as lagging or minus 120, and 120. Next, we set up our open delta. We will do this by having the channel 2 voltage, which is in our case here is VB, lead the channel 1 voltage, VA, by 60 degrees. Here we are using VA and VB channels. Let's take a little closer look at what we saw on the test equipment in the previous slide. You'll notice here that we have a depiction on the left of almost the exact same vector diagram you were looking at off of the test equipment. To the right actually shows the test equipment itself. This shows 3 different sets of channels, the V1, V2, V3, and then I1, I2, I3. Depending on your test equipment, how this is labeled and some of the nuances will be a little different. To the left of the test equipment here, we basically see some terminals, VA, VB, VC, VN, IA, IB, and IC. These are simulating what you would see on a protective relay or a meter that you'd be connecting the test equipment to. And as we said before, what you're going to see here is the same thing on the previous slide. However, what I wanted to point out here specifically has to do with the voltage connections on the relay. Most relays for switchgear and meters will have a designation similar to this, VA, VB, VC, and VN. It allows for a Y-connected set of PTs, a delta-connected set of PTs, or an open delta-connected set of PTs. So in this case here, we're using our open delta. So at VA, we put our first channel and we set it at 30 degrees with an amplitude of 120 volts. On VB, it's a little different. VB is basically going to be at 0 reference or neutral. You'll see it down in the middle of the vector diagram on the left. And you'll notice that VB is jumpered to VN. This is very important that you do this or you're not going to get good readings. You jumper your VB to VN, and both your returns or your neutrals on your 2 voltages, your V1 and V2 voltages, are tied together here. And then VC will come off of your second voltage source, V2, which is set leading V1 by 60 degrees, or in this case, 90 degrees. Now again, the reason why we're using 30 and 90 instead of 0 and 60 is our CTs are Y connected, and we want to account for the fact that those currents are going to lag the voltages by 30 degrees, so we set it up to start this way. So now we're going to examine how we get balanced 3-phase to phase voltage from these 2 60-degree separated vectors. So we're going to start with the VAB development. Now keep in mind that on vector resultant vectors, we're going to always go in the direction of the first element listed. In this case, VA direction for VAB development. Well, if you look at, since VB is at the neutral point and VA, you can see that VAB is going to be exactly the same as the VA vector. So the VAB voltage will be the same as VAB heading out in the direction of VA. Here we're going to look at the VBC development. So VBC, we're going to be using VB and VC as indicated in the arrow, and again we want to go in the direction of VB. Since VB is at the neutral point, that would be the direction of VB. So we take this vector that's depicted by this arrow and we move it down so its origin is at VB, and it looks like this, and this becomes our VBC vector. Now let's look at our final vector, which is our VCA vector. As you'll see, we're going to be using VA and VC. However, the direction, since VC is the first element, is going to be VCA. So the VCA vector looks like this. Here we tie these 2 points together, as shown by this arrow, but we got to move it. So we move this vector over to where, again, we got our origin down here at the center at VB, and the vector heads out and goes in the direction of C, which gives us our VCA vector. So what you end up with is a perfectly balanced 3 phase-to-phase system of VAB, VBC, and VCA developed off of 2 AC sources, VA and VC, as shown here. Now we used channel 1 and channel 2, source 1 or V1 and V2. It don't matter which one you use as long as the angular relationship is there. Now let's see how this looks on our test equipment and our relay set. On the left is a device overview of the metering on the relay that we are injecting the voltages and currents as I showed you before in the previous slides. Now, what I did here was I went in and I programmed the PT and CT ratios to 1 so that what you're seeing is directly related to what we're putting in with the test equipment. In other words, on the currents, I'm putting in approximately 0.50 amps and the voltage is approximately 120 volts. So it'll actually show you this, so that's why your kW and kVAR and kVA and all that will be low. So again, this is just as we showed before. However, what's going to look different to you on the vectors on the right side, you're going to notice that before on all the vectors I've been showing you from the test equipment standpoint, VAB was at 30 degrees. That's not the case here. The reason is this piece of this relay uses the VAB as a reference. So it changes everything to be in relationship to VAB. So we still have the 30 degrees shift between IA and VAB. You'll see that IA at unity, or 1.0 power factor, IA is lagging VAB by approximately 30 degrees. IB is lagging VBC by approximately 30 degrees, and IC is lagging VCA by approximately 30 degrees. So what happens is, this is again unity, and if you'll notice to the left side, at your P, which is your power, your Q, which is your VARs, and your S, which is basically your VA, you'll notice that we're showing a 0.99 power factor, which is what we were expecting, 1.0. We're showing that kVA is equal to kW, which it is at unity, and we have basically 0 VARs. Now let's take a quick look at what would happen if we had a lagging power factor. A 0.86 lagging power factor means that we have 30 degrees displacement of current lagging voltage. This would be into an inductive load. So you'll notice our currents on the left are the same, 0.5. Our voltages to the right of that are the same at 120. You'll notice, however, that our power factor is saying it's 0.91. Now that's a little off from what we were expecting, but sometimes these things have trouble. The metering on a protective relay like this isn't perfect. It's close, but it's not perfect. But it's important to document what it's seeing. So it's telling me that I have a 0.91 power factor. You'll notice that kVA and kW don't equal each other anymore. There's a little difference, kVA and kV. And you'll notice we now have some kVARs. That's because of the shift in the power factor. You'll also notice that whereas IA lagged VAB by 30 degrees at unity, IA now lags VAB by approximately 60 degrees at our 0.86 power factor. This completes our tech byte for protection and control on theory and math and the simulation of the open delta potential transformer configuration. I want to clarify just a little bit about the open delta as used with protection and control and metering. In the previous slide, we talked about the fact that the power factor wasn't exactly 0.86. Some of the currents vectors looked a little off and such. There's not only issues with some metering errors that should be pretty minute normally, but when you use an open delta configuration, because there's algorithms in the relay that have to do the calculations to create these vectors, what happens is you sometimes have some inaccuracies built in. And quite honestly, the Open Delta is not a good choice for detailed and accurate metering. So that'll be covered in some more advanced engineering related discussion about the Open Delta transformers. But just understand that we're looking for this to be close right now. The goal here is to teach you how to use your test equipment to generate what you need to test a relay using the Open Delta. Always document the values accurately so we understand any nuance issues that might exist in case they're way out of tolerance. Hope this has been really helpful to you guys. Take care, be safe.